Studies have shown that being in one position for too long can have adverse health effects, such as cardiovascular and joint disorders. However, not all work environments have adequate seating for their workers. Our solution is based around the idea of a knee brace that can help support a portion of the worker's body weight. We took inspiration from the flamingo, which can lock its ankle joint and balance using very little energy. And we also looked at existing solutions with similar designs, such as the Noni. However, they are prohibitively expensive and not readily available to the general public. After researching foldable mechanisms, we selected the SARS linkage due to its good range of motion and the ability to lock, which was crucial for our application. Our initial prototypes used 5-layer laminate manufacturing made using cardboard and polyester. Using Python scripting libraries, cut patterns were generated for both the rigid and flexible layers, which are laser cut and laminated together to form the completed mechanism or part. Our second prototype was physically larger for more range of motion and was the first attempt at integrating servo actuation. We also designed and 3D printed a knee brace to attach the mechanism to. However, the wires used prevented the mechanism from taking advantage of that full range of motion, and the size of the mechanism meant that it would no longer fit behind the knee. We then shrunk our mechanism back down and began using fiberglass for increased strength. This next iteration had a new issue where the attachment links had to be extended and introduced significant deflection. The solution was to shorten these links, which reduced the range of motion slightly, but not enough to be detrimental. Even though we sacrificed a slight range of motion, the mechanism gained considerable strength and was able to hold over 140 pounds without breaking. We also tested the SARS linkages by themselves to see their load-bearing capacity. The cardboard couldn't withstand 10 pounds, the lowest weight we could possibly test. However, the fiberglass fared much better and was able to withstand up to 34 pounds before failure. The main mode of failure for both the cardboard and the fiberglass was delamination. Now that we knew our mechanism could withstand significant loads, we looked to incorporate actuation into the device. Using a geared motor instead of a stepper motor and high tensile strength string instead of wire, we were able to achieve locking actuation while retaining full range of motion. We needed to know the state of the device before we attempted to lock or unlock it. Failure to do so could result in damage to the mechanism. Using the inputs from the magnetic field sensors, the device waits to lock at the appropriate position. To make the device smarter, we used acceleration data from an onboard IMU to determine when a person is about to sit, so that it can lock to support their weight. The user can choose when to lock the device using the switch. The final step was to test it on a person. The user was able to switch between locked and unlocked states at will, and reported that despite there being only one knee brace, they could feel it providing some level of support. The next steps for this project is to create a second knee brace and continue testing. We feel that this design shows promise. It is significantly cheaper to replicate than the next competitive solution, and is much more simple to manufacture. Preliminary testing shows that one mechanism alone can support at least 140 pounds. Therefore, 2 knee braces could potentially be more than enough to support the average human weight. However, more testing and analysis still needs to be done to ensure the safety of the user and the overall effectiveness of the system.